give an introduction to some theory of rectifiable subsets of a metric space. I have some lecture notes here at this URL. This has lots more detail than what I'm going to cover in the lectures. And where the details, where things get really detailed, I'll probably just draw a picture rather than go through the exact details, just because I think it's much more helpful in this type of a course than to go through all the details. Right, so how the course will split is basically today I want to talk about rectifiable subsets of a metric space in terms of the results of Ambrosio and Kirkheim on the properties of rectifiable subsets. And then the other 3 hours, so the other after today, to talk about sufficient conditions for a set to be rectifiable. So we'll see that today's lecture somehow follows very naturally from classical geometric measure theory. Basically, we need to prove a Rademacher's theorem, and then we get properties of rectifiable metric spaces. But the conditions for rectifiability are quite different. They are motivated by the classical geometric measure theory, but the proof strategy for them is quite different, because the classical proofs really are rooted on the ambient Euclidean structure, which we'll see that we don't have any. Okay. So throughout the whole course, XD will be a fixed metric space, and we assume it's complete. Okay. So the motivation for studying rectifiable subsets of a metric space is simply, it boils down to basically the fact that it's quite easy to define what a rectifiable subset is, because simply, I'll write down the formal definition right now, but just from the classical definition, in order to define a rectifiable set, what do you need? You need a Lipschitz map. And you need Hausdorff measure. Okay, and so, of course, these two things are easily defined in any metric space. So the fact that we can define what a metric space is, what a rectifiable subset of a metric space is, it is even included in Federer's book, right? So it's a very natural question to ask, what are the properties of rectifiable subsets of a metric space? And we just have to prove, the properties that we want. So, So it's easy to define what a rectifiable set is, but the interesting question is, can we, well, let's just say, what are their properties? So just so that it's clear what I'm talking about. So, definition. A subset E of X, let's say it's REL, is n-rectifiable if there exist countably many Lipschitz maps that are defined on some subset of Rn into X that cover almost all of E. So if we take E without these images, this has Hausdorff measure 0. Okay, so if you've never seen the notion of a rectifiable set before, even in Euclidean space, basically the motivating definition, the motivation behind this is this is somehow like a Lipschitz manifold, right? Each of these pieces you could consider as, a Lipschitz surface. We allow countable unions and to exclude a set of measure 0 because then it really allows us to use measure theory to do geometric constructions in a way that's simply only asking for one parametrization, or maybe finitely many, or finite overlaps. That's a bit too restrictive. Whereas allowing the full countable union and sets of measure 0 allows a lot more tools of measure theory to try to do some geometry with this type of problem. Okay, so now.
Do you assume the AI to be Borel or not?
No, okay, so that's a good question. So right now we don't assume anything. Because X is complete, you may suppose that they are compact, because you can always extend the Lipschitz map to the closure of a set. So since X is complete, we may suppose the AI are compact. If X is not complete, then all bets are off. But so the reason why I assume completeness is simply because I don't want to try and do anything inside the Vitali set, or inside a Vitali set, right? That's a bit too, like by a Vitali set I mean the non-measurable subset of the real line. I don't want that to be X. So if we assume completeness, you may think that's a bit too far, but then Borel subsets of this are also okay. So kind of just assuming a complete metric space is a complete ambient metric space is the right level of regularity to not encounter the Vitali set. Right, and then that's what allows us to take compact AI. Equivalently, I suppose you could drop completeness from X and then ask that the AI are compact, and you probably obtain the same theory. Okay. Now, if X is a Banach space, then you may suppose that the AI are all Rn. So if X is a Euclidean space, this is given by the McShane extension theorem, right? Because what it says is that and this is given as an exercise in the lecture notes. Basically, the McShane extension theorem allows you to extend any real valued Lipschitz function to a whole to any superset. So that means that if you have a finite dimensional X, you can extend all of the FIs to Rn, and there's no problem. If X is infinite dimensional, then there's a theorem of Johnson, Lindenstrauss, and Shetman that says you can always extend Lipschitz maps into Banach spaces. defined on Euclidean space. So somehow, the reason why in this definition I ask for subsets is simply to rule out topological obstructions in X. Right? It may be that X has a very nice metric theory, but for topological reasons, it doesn't contain Lipschitz images of all of Rn, but if we allow subsets, then we get a nice theory, and the two definitions are equivalent if X is a Banach space. And in fact, this idea goes a bit further, so kind of going further. Right. So any metric space can always be isometrically embedded into a Banach space. So if X is separable, then the Kuratowski embedding isometrically embeds any, let's say, separable metric space into an infinity. Right. So, I guess I'm starting with a bit of a philosophical point of view about all of this, but I think it's worth a digression. So, if I have any metric space, I can put it into a Banach space. And then, well, in that Banach space, I could just take all of my AIs to be Rn. So then you may ask me, well, why am I bothering with this subset definition if I could just always put Rn here? And in practice, one swaps between the two definitions. Okay, but there's actually there's a reason not to put everything in L infinity. Okay, so we have kind of two scenarios. Either we work with a general metric space, right, and then we have Fs that are defined on subsets, or we could just consider everything to live inside L infinity, and then have F defined on Rn into X. Right. But they're equivalent. So this okay. So this case, when you just consider X, is the intrinsic approach. And in my opinion, it's the much more geometric way of doing things. But this requires us to take subsets. Right? And then, of course, we have the L infinity case, which is the extrinsic case. So, from a technical point of view, this is often the simpler way of doing things. Right, but it can also be quite misleading. Just to give you, again, just to kind of make this a bit more concrete.
Can you give an example why it's misleading?
Yeah, I will do that in a second, yeah. So the one option, the one thing to keep in mind of why we need to take subsets is if E is equal to X is a positive measure Cantor set. Right. So this is the if you just look at things from an intrinsic point of view, so you only know about the Cantor set. Of course, in practice, we know that actually X is a subset of R, but this is the extrinsic approach. Right, now over here, according to the classical definition of rectifiability, which is where which is what many people may have seen, where we take all of Rn here. This guy is rectifiable, right? Because, well, we can cover it by the entire line. Whereas within itself, it's not contained in a countable union of Lipschitz images of R, right? So it's not in a Lipschitz image or countably many. Lipschitz. So, of course, we still want the positive measure Cantor set to be rectifiable as a subset of itself, which is why we have to allow for the subsets over here.
Can I ask a question, sorry?
Yeah.
What is the topological obstruction? You said we avoid topological obstructions, right? So how topology is...
Yeah, exactly. So the positive measure Cantor set, just for topological reasons, it can't be covered by a Lipschitz image of R because it's disconnected, right? So like the metric space may have lots of holes, but provided they are not metric holes, this is still a thick piece of R, even though it has some small holes. So topologically, this would prevent it from being covered by a Lipschitz image of R, but not by a Lipschitz image of a subset of R, because it's just covered by itself. Maybe I should even draw a Cantor set. So if I have a positive measure subset of R, right? Right, we want this to continue being a rectifiable subset of itself. Okay, so now the misleading example here, there's obviously quite a few as well. So this is, let me come back to this, so misleading. So if you want a one-line example of a misleading rectifiable subset of a Banach space, you consider the characteristic function, so if you consider the set characteristic of 0t such that t is in 0, 1, right? And this is a subset of L1 of 0, 1. I think I have this right. So this is isometric to the interval. This is isometric to 0, 1. But it's actually a very unpleasant set. It might not be straightforward to see it from here, so I'll give a much easier example to see. So, in my opinion, a better example is the following. This is in L infinity. Right, so I'm going to write L infinity as R times L infinity. Right? So now I want to look at the set. So in the first component, I have T. And in the second component, right, so this is, let me just in case, this is all bounded sequences with the supreme of norm. So here I get to specify a sequence. So I'm going to just write down the nth component of the sequence. The nth component will be 1 over n sine nt. Okay? So that t is in 0, 1. So again, this is isometric to 0, 1. But now let's look at the graph. Like let's look at what this set looks like. On the x-axis, I'll plot the first component. Right? So this is just 0, 1. This is a t variable. And in this direction, I'll plot the nth component. So of course, this oscillates more and more as n increases, right? So we have its amplitude decreases, but its oscillation increases. So inside L infinity, this has no notion of a tangent, for example, inside L infinity. So although L infinity has linear structure, it doesn't really help you with this example. But from a metric point of view, this is the nicest possible set that you can have, right? Because this is just an interval. Right? So although the ambient space has linear structure, it doesn't have use to describe the geometry. Okay. Oh, sorry. I'm not sure how to fix that. So basically, kind of, for today, we will see that just for technical reasons, we will use somehow the linear structure, but in the following lectures we won't, because it won't help us in the following lectures. Okay. So, right. So the purpose of today is to prove Rademacher's theorem. So whenever I say classical geometric measure theory, I always refer to X being a Euclidean space. So classical. This means X is Rn. So classically, the justification for studying rectifiable sets is due to Rademacher's theorem. So, which means that the geometry of rectifiable sets. So, for example, the existence of approximate tangent planes. Is provided by Rademacher's theorem. Which, just to remind you, says that every Lipschitz f defined on Rn into Rn is differentiable almost everywhere. Right, and basically, okay, that gives a tangent of any one of those fi's, right? Because that's what the derivative is. And then it's just measure theory to kind of show that you don't get interference from the other pieces at almost every point. At least when the set has finite measure. And we need a corresponding statement for the metric space example if we are to try to do any type of geometric consideration of rectifiable subsets of a metric space. And so, indeed, we do have a metric Rademacher theorem. This was proven by Ambrosio and Kirchheim. So we have a metric This is provided by Ambrosio and Kirchheim independently for dimension 1, and then Kirchheim's work also works for higher dimensions. And so that's what I'm going to go through today. Of course, a substantial part of this is what does this even mean? Right? What does it mean to differentiate a metric space valued map? Right? And indeed, once you have the right definition, the proof is actually similar. It's a modification of the classical proof, and really the hard part is to come up with the right definition. So, an interesting first question. Is what do we mean by a derivative of f that's defined on, let's say it's defined on Rn and it goes into x. Okay. So I'll start off with the one-dimensional case. So let's say this is our rectifiable curves. So definition. So we have two notions that are, they are straight out of the classical theory. So if gamma is a Lipschitz curve, so you see here already I'm taking the case when I'm defined on a connected set, but like by the preceding discussion, right, we can always reduce to this case. And just from a technical point of view, it's easier to handle when we have the domain being a whole integral. Okay, but the general case follows by embeddings. So the variation of gamma is supremum over, just like the classical definition, it's the supremum over all partitions of distances between points in the curves. Such that A is less than 3, this is equal to 1. One is less than 2. Okay, so this definition, of course, is easy to just modify from the classical definition. Now, for what do we mean by a derivative? In the one-dimensional case, it is given by the metric speed. So the metric speed of gamma at t is the limit as x goes to t of the distance between the 2 points. If the limit exists.
Is motion, so was it not known before Rademacher?
Surely, yes. Yeah, I imagine so.
So,
This
yeah.
is just what we need for the proof.
Yeah, and so, but the statement of Rademacher theorem in dimension 1 was not known before.
My understanding was that Ambrosio was the first one to do this, but I could be wrong. I'd be happy to be corrected. I think surely the higher dimensional version was due to Kirchhoff. Yeah. Right.
Can I ask a question?
Yeah.
So what are the approximate tangent planes of the Cantor set?
The real line. Yeah, because if you take a density, I mean, this is of a positive measure Cantor set, right? So at any density point, it almost looks like a line if you zoom in. And yeah, and that's really at the heart of rectifiability. If you zoom into a density point, you basically see a linear image of Euclidean space. Yeah. Of course, you just have to cook up the definition so that it's correct. But it's a sensible definition, trust me. Yeah. Okay. Right. So I guess the first result is that we have the one-dimensional Rademacher. And as I said, this, to my knowledge, this was first by Ambrosio for even functions of absolutely continuous functions, and it's also in Kirchhoff's paper. So if we have gammas above, right, then the metric derivative exists almost everywhere, and we have that the variation is given by integrating the metric speed. Right, so this is a fundamental theme of calculus, right? It's a metric fundamental theme of calculus. Okay, so I'll go through the proof quickly. So the idea of the proof is it basically boils down to two facts. So the idea is that distances can be realized. So distances in this metric space are distances so the distance between any 2 points is realized by distances to a dense subset. So they are realized. To a fixed dense set. right? But these functions are differentiable by classical Rademacher, just by composition, right? But so let's say distance to xn. But these functions, when composed with gamma, this is differentiable almost everywhere by classical Rademacher. Okay, and that's basically enough to conclude the proof. So I'll go through the details now, but this is the idea to keep in mind. Right. So indeed, so let xn be a dense of that thing. Right, and set phi n. Where do I want this? From AB to R to just take so this function is real to real, and is Lipschitz, right? So this is differentiable almost everywhere. This is differentiable by, in fact, so the real to real case is really it's not even Rademacher's theorem; it's by Lebeck's theorem. But so it is differentiable almost everywhere, and of course, almost everywhere we can suppose that all of them are differentiable, right? Just because this is just countably many n. So that means that for almost every t, we can define m of t to be the supremum of this metric. Of the supremum of the derivatives. For almost everything. Right, we will show that this is actually the metric derivative. So I'll just run through this because we have to prove two inequalities and both of them are rather straightforward. Right, so for the first inequality, what do we do? Right, so since x goes to distance, since this is Lipschitz, well there's one Lipschitz, and this is most phi n. Yeah, so if I put a limit here, we get this, and right now, almost let's say we're at a point where we can make that definition. This is equal to phi n prime delta t. So we can take a supremum and we get one of the inequalities that we require. We get that this is the other inequality. And so, if I have any two fixed points S and T, so this quantity is always greater than this, right, even with an absolute value. Simply by the triangle inequality, this is always greater than this. But if I take a supremum over n, then I obtain equality, right? Because, for example, I can just take a sequence of xn's that converges to gamma of s. This goes to 0, and this becomes the left-hand side, right? So this is equal to the supremum over n of this. Right. And just to rewrite it in terms of the other definition, this is phi n of s, and this is phi n of t. Okay. And now, to this difference, I want to apply the fundamental theorem of calculus. Right, so this is at most the integral from s to t of the derivative of phi n. This should be a different variable. And this is at most integral s to t of m of t. So, final step is that if we take a Lebesgue point of m, then we get the other inequality that we want. Right? Because at a Lebesgue point, at a Lebesgue density point, this would converge to m of t. Right? So, if t is a Lebesgue point of m, we get the other inequality. Okay. So I'll skip the proof of the fundamental theorem of calculus. If someone is interested, it's all in the notes. But because I'd like to prove the high-dimensional version before the end of the lecture. But you see, just once we have the right definition, the proof is not that hard. Right? In fact, we constantly rely on falling back to the classical Rademacher theorem in order to prove the metric version. Okay. And I'll also just mention that once we have a derivative, by essentially the classical proof, you can then parameterize any such gamma by arc length. Right? The proof is the classical proof. You just need to know. Again, it's just a matter of the right definition. But once you have a derivative, you can then you can just reparameterize any curve so that its metric speed is 1 almost everywhere. Maybe I'll just make a mention. We can reparameterize arc length by the classical proof. Well, I guess it depends on which classical proof you have in mind. Okay. So now I will talk about the higher dimensional case. Are there any questions about this? Okay. So higher dimensions. Okay, so as I said before, this is due to Kethlein in 94. So now we have to think a little bit more about the definition of a derivative. Right? So of course all we have to play with are distances. So we don't get vectors, but we can measure distances. And it turns out that the right thing here is to consider norms as a replacement for the derivative. So let's say we have our Lipschitz map. Right. So a metric derivative of f at x is a semi-norm which I will call absolute value of df at x on Rn such that, so I'll write down something that looks slightly stronger than what one's first guess would be, but it's just that you're able to get something stronger out of the proof. So such that the limit as y and z go to x of distance between f of y, f of z, minus this norm applied to y minus z divided by, so now of course we need the distance on the bottom, but we need to take the distance of y to x plus the norm of z to x. Okay, so such that this is equal to 0. Now, just to say, right, so I guess I have two remarks. One is that, so what is this norm doing? This norm is telling you how much the map stretches in a certain direction, right? A first guess might be to only consider this when z is equal to x. So you would have x, and then this would disappear. And so you're only looking at how the map stretches pointing out of x. Right? But what this actually tells you is that you have your point x here, then you can also tell how much your map stretches between these 2 points. But it's still only in terms of the distances to x, right? It's not in terms of the distances between the 2 points. That's more like a C2 control, I guess, rather than a C1 control, which is more like Lipschitz.
So you get a different notion if you just use x for z, yeah?
Yeah, you don't. It's not quite strong enough to prove the properties of rectifiable sets that I'll mention at the very end, because this is more like, well, they're equivalent. Yeah. Up to a set of measures, they're equivalent, but the version that you really want is this one. Okay, so just as a remark, if f goes from Rm to Rm, then the metric derivative of this is given by, so this is a norm on Rn, so it has to be the vector. This is just given by the norm of df. So if this is differentiable, then its metric derivative is just given by putting the absolute values around. the regular derivative. Okay. So I guess I can put this theorem at the bottom here, which is that every Lipschitz f from Rn to x is metrically differentiable almost everywhere. Okay. And I'll just give a very quick sketch of the proof. So just like the classical Rademacher theorem, we fall back to the one-dimensional case, right, by Fubini, basically. So let un be a dense subset of the sphere. Right, by the 1D case, we can define df at x in the direction of um to be the limit df x plus t um So this exists for almost every x and for every m, right? For almost every x and for every m, we can define this thing. A straightforward calculation shows that this is Lipschitz in this variable, right? This is Lipschitz in this variable. Simply because f is Lipschitz, it gives you that this is Lipschitz. Okay, so we can extend it to the whole sphere. And so there exists a unique extension to S n minus 1. I mentioned this at the very start, that you can also extend a Lipschitz map to the closure uniquely. In fact, uniform continuity is enough for this. And then we can extend to Rn by just scaling. And now this is the part where I go a bit sketchy. So now, right. So provided you're slightly careful, this map that takes x to this quantity is a Borel map, right? So x goes to equal L. This is just, I mean, with respect to the right type of metric on the image, but that's not really a problem. By Lusin's theorem, we can suppose it's continuous on a compact set, right? And it suffices to prove the result for a density point of that compact set. So by Lusin, right, it suffices to prove the result for x, a density point of a compact set on which the f is continuous. Okay. And so now, so what you actually prove is something slightly stronger, and then I'll draw a picture of why it's true, right? In fact, for such an x, we have that the limit as t goes to 0 of I'll draw a picture in a second, and this is uniform in U and U prime in uniball. So let me draw you a picture. Okay, so here is X. And this is where it should start looking like, you know, one of the many classical proofs of Rademacher's theorem. So I have this point x plus tu. I have x plus tu prime. And I want to estimate this difference. Well, because x is a density point of my compact set, I can find another point y here that belongs to, right, let me just say, I want a letter for this compact set K. So I can make sure that y is in K intersects a ball around this point of radius epsilon t. Right, simply because what x is a density point of K, I can always find this point here. Otherwise I'd have a large hole. Right? But now because y is in K, I can have a derivative. Okay, I should have assumed some further uniformness of this derivative, I guess. But the point is that because y is a good point, I can now find a derivative in this direction. Right. So this is a derivative in a direction close to u minus u prime. Right, and so if I want to estimate the difference of f between these 2 points, it suffices to check the distance of f between these 2 points, and that's given by the one-dimensional Rademacher theorem. Right, I'm missing quite a few details, but simply by measure theory, we try to resolve to the case that looks like a classical proof of Rademacher. We just have to forget that we don't have vector space structure. Right. Okay, and if you just give me 2 seconds, I just want to mention a corollary of this, because it's actually the local structure of rectifiable sets. So if E is n-rectifiable, finite Hausdorff measure, then for almost every point, the Hausdorff density of E exists and it's equal to 1. Okay, so how do you prove this? It's by the area formula in the same way as how you would prove it for classical rectifiable sets. Once you have Rademacher theorem, and
Shouldn't you divide by the previous what should the
oh yeah, it depends what your definition of Hausdorff measure is. I guess but let's put it right. And the question is the converse true? And in dimension 1 it is known, and it's known if x is so n is 1, yes, and if x is Rm with a strictly convex norm. But this is the classical case, right? So classically, when on Euclidean space, this is due to Marstrand and Mattila. The proof works for strictly convex norms, but other than that, the question is completely open, right? And that's where I'll leave it today. Thank you for your attention.